So, since this is in the way, I'll write this one out. So when I look at the circuit, here's my circuit here. So I have two switches here. So the first switch, what it does here is that it closes at t equal to 0. And then I have a second switch that closes at t equal to 51 milliseconds. Our goal here is to determine this current, I12, as a function of t. So what do I want? I want you to calculate this current. From this current, plot this current, but also interpret it first, right? Always interpret to make sure that you're moving in the same direction. Yes?
Can we go back to the circuit network series formula? I think there's no minus T1. Could you set up VC2 T2 equal VC3 T2?
Say that one more time.
VC2 of T2 should equal VC3 of T2. Because the voltage can't change instantaneously. So we can set up.
Here, let's not go over that right now. Because I agree that we can discuss this a little bit further, but
No, I mean, because the voltage across the capacitor can't change instantaneously. So when we calculate the voltage for circuit 2 at t equals t2, will be the same as we calculate
that,
that point.
that voltage at this one point.
Yeah, use both formulas for t equals t2.
Yeah, because you already used the formula that's shifted.
If you plug in t equals t2 to the third formula, it will be the same.
So this is already shifted to T1.
Right, so if you used that shifted formula to calculate that value at T2, then you wouldn't have to shift it again. Except I think I just made it Max's argument then.
If you were to shift it like back further, then essentially you're going to have kind of starting before 0, and that doesn't really make physical sense to me.
That doesn't make any sense either. Like I said, I mean, in my head I was thinking T2, but
Yet in
I'm going to leave it.
in my notes
Let's
from
go. We can discuss this later. I think we got to march through these problems. Okay. Not that I want to avoid it. I'm just saying that we got to march through these examples. I think that's a subtle point here. Hey, let's start looking at this thing. Okay. So the first thing I want to do here is that I want to try to understand the behavior of the circuit before we start getting into the math. Okay, remember, I think this is important practice, right? Figure out what the hell is going on. Okay, so at T0 minus, this is closed, this is open. So what I'm seeing here is that this inductor here is seeing the current coming through here, here, and then you can see that it's divided. So the current through the inductor is going to be the current through this 2 ohm resistor. Okay? So now what happens? So what we're seeing here, if I could say this, at t equal to 0 minus, we say that the inductor sees the full 52 volts. Right, there's only one source, but what you'll find here is then at t equal to 0 plus, this thing is now gone. So there's no source in the circuit here. If there's no source in the circuit, what I'm seeing here is that I have a switch like this, and as the current through the inductor is coming down, you could see that what's happening here is that if this is closed and this is closed, it's now seeing its current being divided by these two. Right? It's decaying, of course, because there's no source. But I'm seeing that this guy's having the current being divided. Now, what happens? This thing opens. Right? If this thing opens, this guy's gone, and then I have this guy right here. So all of a sudden, instead of dividing the current, it's actually having the current go through one loop here. So what I'm seeing here is that between 0t and 51 milliseconds, we have VOC is equal to 0. There's no source. So this implies here that the inductor decays. As the inductor decays, we're seeing that there's a division between the current. Right? So if I'm looking at that 12 ohm resistor here, what I'm seeing here, it's only seeing part of the current. Right? Because it's dividing the current relative to that 12 ohm resistor. As soon as this thing opens, what happens? It's seeing the full current. So the question is this. This guy, before this switch is open here, I would expect it to see less current. But as soon as this thing gets open, I'm expecting to see more current from the inductor, right? Because it's not dividing the current. So what I would say here, intuitively, I would say that the 12 ohm sees less current due to, being divided. Whereas for t greater than 51 milliseconds, again, VOC is 0. It's still decaying. But now, what you're seeing here is that the 12 ohm sees all of the inductor's current. So, in general, what I find here is that you might see a spike. Okay? You might see a spike in current. If there's suddenly less resistance, you'll see more current. If you suddenly have more resistance, you'll see less current in certain circuits. But here, because the current's not being divided now, then I'm expecting something like that. So, here we go. Let's do it. So the first thing that I'm going to do here is that I'm going to call my first circuit number 0, and that's because t is less than 0 minus. So remember, it's in steady state. So here I go. I look at my circuit here, and this is what I have. I have V, I got 6, 12, 6, and then I have a short right here. Right? So right here, I have my current at 0 minus. So when I look at this guy here, I'm going to get 6, 12, then I got 6, 2, and I need that current. But I'm going to look at two currents simultaneously now. Because ultimately, we want to calculate the current of the 12 ohm resistor, so I'm going to look at this guy right now. I12 0 minus. Okay, I'm going to look at two currents. So the first thing that I'm going to do here is that there's a couple of ways to solve for this. What would I probably do? I'd probably use voltage divider rule. Okay? So I would get the voltage across this guy right here, and then I would calculate the current by dividing by 2 ohms. So I'm going to use VDR to get voltage of the 2 ohm resistor. So if I do that, then I'm going to do V2 ohms, going to be, remember these guys are in parallel, so I got 2 parallel to 6, which means since it's a third, it would be 6 over 4, so that should be 3.2. And then I'm going to do 6, and then adding these two gives me 18, and then I'm going to do 52. So when I calculate that voltage, what did I get? I got 4 volts. If I got 4 volts, that means that the current of the inductor at 0 minus is the same as the current of the 2 ohm at 0 minus, which would be 4 divided by 2, so I get 2 amps. Okay? Assuming that my numbers work here. So, in a very analogous way here, I can calculate I12, right? If I know this voltage, then I know that that's 4. These guys have to see what? 48? You guys with me? Okay, if it sees 48, then I could say that using VDR to get V12 at 0 minus, I could say that V12 is then going to be 12 over 6 plus 12 times 48, and I get a voltage at the end of 32 volts, which then tells me that the current across the 12 ohm resistor will then be 32 divided by 12, which I get a value of 2.67 amps. Okay. So now I got my two currents. Circuit number 1. What happens now? Switch is thrown. This switch is thrown here, kills everything else, so now I have a decaying circuit. So now I'm at circuit. Shit, I don't even know how to spell circuit. So now I'm between 0, t, and 51 milliseconds. So when I look at this circuit here, this is what I have. So this is 12, 2, 6. So what we do know here is that if I look at this guy here, IL, we know that that's what we're looking at, but we're really looking for that guy at the end. Let's go calculate the current of the inductor. So what do I know about the current of the inductor? We know that the current of the inductor must look like this. Well, that's that tau right there. So when I look at this guy, no source, right? So because I have no sources, that implies that I short circuit must be 0. So when I look at my current of this guy here, it's got to be IL of 0 minus e to the minus t over tau 1. Right? That's what it has to be. So I know what that guy is. The only thing I'm left with is I got to calculate tau. Let's go calculate tau. So we need to determine 1 over tau. So what do we remember about 1 over tau? So remember, 1 over tau is L over R of N, which will then be Rn L. So I got to go calculate the Thevenin resistance. So what do? Let's see if we can do this here. So I'm going to remove my load, and then if I follow the current, you can see this is going to be 2, and then these two are in parallel, and it comes back all the way around. So if I look at the Rn resistance here, my circuit looks like this here. So this is a 12, a 6, a 2, and we're calculating this guy right here. So if I look at Rn, Rn is going to be 2 plus 12, 6, half, divided by 3 gives me 4. This should give me 6 ohms for Rn. So now I got Rn. So what do I do with this? I'm now going to calculate 1 over tau. So if I look at 1 over tau, I'm going to get Rn over L. So this is going to be 6. And then we have a 1 Henry inductor. So therefore, I get 6 hertz for 1 over tau. I should call that tau 1. Okay? So then, what does my solution for the inductor look like? So the inductor current is IL1, right? I should be labeling this with a 1. So T has to be IL at 0 minus e to the minus 1 over tau 1 like this. So this gives me, I know my inductor current is 2 amps. So I got 2 amps times e to this guy here, which will be minus 6t. So this is my inductor current between 0t and 0.051 seconds. So now I got my current of the inductor. So far, this is not a surprise here. We would expect this guy to come all the way down and decay, just like this here. But what we want to do now is that we want to calculate I12 ohms between 0 and 51 milliseconds here. So let's look at the circuit here. So if I look at the circuit and I follow the current, what is the current doing? Well, the current's coming all along here, and then what does it do? It splits. Now, I'm not saying that this is the source, but it's sort of like producing the current in the circuit, right? It's leaking out of this inductor, if I could say that. So that means then I could use a current divider rule to figure out the current of this 12 ohm resistor here. Right? So this is what we're after right there. So when I look at this here, I'm going to use CDR to determine I12. So here we go. So then I12, according to this, should be what? The opposite resistor divided by the sum. So it's the opposite resistor. In this case, it's going to be 6 divided by the sum times the current source. And the current source in this case would be IL1 at this time that we have right here. So when I look at this guy here, this should be, so I'm going to get 18 and 6, so I'm going to get 1/3. So then I should get 2/3 of e to the minus 6t amps for I12 between these values here. Okay, I'm getting too small. I'm going to write this bigger here. So this should be 2/3 e to the minus 6t, and this is I12 between 0t and 51 milliseconds. Okay, I'm getting right at the end, so I got to move back that way. Okay, so now we're on our third circuit. What's happening? This switch is opening. So as that switch is opened here, I now have my circuit number 3. And this is for t greater than 51 milliseconds. So now if that switch is thrown open, that means that this 6 ohm resistor is gone. So now what my circuit looks like, it looks like this. It's a 12, a 2, and then I have my inductor. So I have my 12, my 2, and then I have IL of 2 of t is what's pushing that current through here. And right away, you can see here, since I have one loop, that the current of the 12 ohm resistor is the same as the current of the inductor at this IL2 place here. So I got to do the exact same thing now. So when I look at this So the solution here that we're seeing here is that L2 of t, let me be careful, for t greater than this guy here, has to be what? I short circuit 2 plus IL1 at t equals to 51 milliseconds, right? That's what the current was initially. Minus I short circuit 2 times e to the minus t, and there's a shift here of 0.051. And now I have a new time constant. So when I look at the circuit again, I need the Norton parameters as before. And the Norton parameters have to be I short circuit 2, but of course that's 0 because why? There's no sources again. So I need to go calculate this new Thevenin or Norton resistance here, and then I need my new time constant. Okay? So when I look at this guy here, we see that this term right here is 0. This term right here is 0. So I'm left with that term and that term. So the first thing that I'm going to do here is I'm going to calculate this guy so I can calculate that guy. So let's calculate this. So let's calculate the Norton resistance. So what do? I pull the inductor out of the circuit, and I have 12, 2. So if I look at this guy, it's clear that Rn here has to be 14 ohms. Which then tells me what tau is. So now if I go over here, then 1 over tau is Rn over L. So in this case, it's 14 over 1 or 14 hertz. Or tau 2 over 1. So now I got all of the Norton parameters, but I got to go calculate this number. Okay? So let's write it all up right now here. So if I come over here and I rewrite this right here, let's write this out. So right now I got IL2 of t greater than 0.051. That has to equal this guy at 15 or 51 milliseconds. So it's got to be IL1 at t equals to 51 milliseconds times e to the minus. Now here's my shift here. So my 1 over tau is 14 now. So I got to write negative 14, and then I have my coordinate shift like this here. So what I got to do next now is that I got to go in and calculate this numerically. So now we want to determine the initial current. So if I do that, I get IL1 at t equals to 51 milliseconds. So then I got to come to the previous current, which was this guy right here. And that guy's going to be what? It's going to be 2 e to the minus 6t, where t is 0.051. So if I calculate this guy, let's see if I calculated it someplace. What I end up getting here is I get, so if I punch that number in, I get 1.473 amps. Okay? So now what I'm going to do here is that I'm going to punch this guy right into here. So I now have this following value. So I have that IL with 2 of t is the same as I12 at t greater than 0.051 must be 1.473 times e to the minus 14 t minus 0.051. amps. And that's my final answer. Okay, that's my final answer. So, let's plot this thing. Let's see if this guy makes any sense here. So what we want to do here is that we want to plot I-12 T. So what I'm going to look at here is that what was the initial value that it started off at? Well, it started off at 2.67 amps. Okay, so if it started off at 2.67 amps, afterwards, when the switch is thrown, you can see that this guy went down to 2/3. So what I'm seeing here is that there has to be a discontinuity. So initially, this guy comes in here, and let's be real careful here. Let's write it properly. I'm going to have I-12 at 0 minus should be 2.67 amps. So now look what happens. At 0 plus, this is the curve. So you can see that it goes from 2.67 amps down to 2/3 of an amp. So what I'm seeing here is that there's a discontinuity, and this discontinuity is coming all the way down to here, and then, I don't know, for the sake of simplicity, we'll say that this is 2/3. Now note, obviously this is not the scale. If it bothers you, squint, maybe it might help. So what you'll see here is that this guy then starts to do what? Decay. And this guy, so at I-12 0 plus, it's 2/3 of an amp. Right? It starts to decay here. And as it starts to decay, then I'm going to say that at this point here, I get 51 milliseconds. So at this point here, if this is 0, this guy's 51 milliseconds, and then the switch gets thrown. So as the switch gets thrown here, I go to this other solution, which is right here. Now, the issue here is that note that at t equals to 51, that term right there kills this exponential so that it's 1. So what happens? At t equal to 51 milliseconds, this whole term goes to 1, and you can see that there's a jump in the current. So then what you're seeing here, that this guy jumps not up to the original value, but it jumps up like somewhere up to here. And then, note that this is negative 14. The other one is negative 6. So what ends up happening? This has to have what? A sharper decay. So then I would think here that this guy decays very quickly compared to that one. So let's be careful with our language again. So note, at this point right here, if I'm on this side of 0, okay, that means I-12 at 51 milliseconds plus, look at my plus, right? My plus here tells me that this guy has to be 1.473 amps. At 51 milliseconds prior to this, at that value right there, it had to be what? I would have to calculate what.
Do you plug in 51 milliseconds for that equation over there? Does that work?
Yeah, that's how we got that.
Doesn't it get the bottom value of that?
Get the bottom value of that.
Okay.
I would
They're
plug
not
in
the
this
same
guy.
because it's a resistor.
Yeah, it's a resistor,
Resistor's
so
current can change.
the current can change. So in this case here, then I would look at this value here, and I would say that I-12 51 milliseconds minus, and that I would have to calculate this. Did I calculate that? I did not calculate it. Okay, but if we plugged in 51 seconds into here, then we would get this value right here, which would then be 2/3 e to the minus 6 times 0.051, and then I would get that curve at that one point. But you're seeing that this got moved, yes?
It's just the inductor put divided by 30 over there.
Say that one more time.
The inductor put at E equal to P1 incident. That value divided by 30 is just that.
Why did you get 3?
Oh, I mean divided by 30.
Yeah, but how did you get 3?
Because the inductor current is 3 times of the 12 ohm resistor current.
But the
And
equation
then
on the right, because it's 2/3.
Yeah.
So you
Oh, yeah,
just
no,
multiply
I'm not, okay, yeah, I totally agree. I just don't have that numerical value. That's all I'm saying. Okay. So now we're left with looking at switches. Yes.
The numerical value is 0.491.
0.491. Thank you. Okay. So now, we're moving on now. So what we're going to do here is that these switches are cumbersome, it turns out. What we'll do now is that we'll write in switches into our voltage sources, but then we're jumping into time-dependent sources. So let me tell you what's going to happen on the quiz next Wednesday. You're going to get one of these circuits. Not necessarily a switch circuit, but you're going to get a constant source for a capacitor inductor. And then the next one is going to be a time-dependent circuit. Okay? The time-dependent circuit is super important because that leads into chapter 9. So we got to be really careful about making sure that we're going to have 2 circuits on Wednesday, and you can call it a mini exam. Okay? Because it's going to take you a shitload of time to do it. Okay, and I will give you that extra time.